Okay. I'm never going to get to the derivation of this gas equation. I'm just trying to avoid it. But I thought, it's got to be boring for you guys to just. I mean, let's do a calculation. I mean, just to have some numbers, right? So let's be in Fetkovich's shoes. 1968, first well producing 10,000 barrels a day from a 10-meter section. Okay? And let's calculate this Reynolds number just to kind of, to think to do it was probably the important thing. But so let's just do this calculation for the fun of it here. Okay? Just to show you. Yeah. Bubble points, it was 4,500 psi, and the drawdown probably was 3,000 psi, 7,000 pound initial pressure. Oh, okay. Okay. Yeah, I made a mistake. Bilal doesn't know he's in trouble. I make a note of the people who are correcting me all the time. So I made a mistake. This pressure here for that equation to apply should really be that bottom flowing pressure is above the bubble. It should be single phase flow throughout the reservoir. So I'd put reservoir pressure there. So that's my first correction. And also, we're not talking about turbulence yet. So, we're postponing that until after Easter, it looks like. But anyway, these equations for gas are assuming Darcy, which is usually not going to be working. But it's just, okay, so now we're going to take just a step back. For the fun of it, Ekofisk, we've got, this is the rate. So we have to calculate a velocity, and let's just take it at 1 foot away from the well. We could do it at the well bore, which is like, just a radius of 6 inches or something. But let's just take it 1 foot away, or let's say call that 0.25 meters. Trying to do this in metric because the Reynolds number is dimensionless. So 10,000 barrels per day. Let's make that metric. How much is that in cubic meters per day, folks? $10,000 divided by, I think there's 6.289. Wasn't that somebody corrected me? Yeah. 6.29 barrels per cubic meter. So that would be 10,000 over 6.29. Yeah, 1,600 standard cubic meters per day. Okay. So I just hope we get a Reynolds number greater than 1. I haven't done this ahead of time. So the Reynolds number is up here. It's dv rho over mu. dv rho over mu. So the velocity is this 1,600 cubic meters per day, right?
It is standard, so you have to divide by
standard cubic meters per day, right? And then we've got this guy that's going to give us kind of equivalent down in the reservoir at some pressure. I'm telling you, this is the BO near the well. Okay, so this is kind of at a pressure at 0.25 meters away from the wellbore. So that's the BO there. 1.6. So it'd be it would be multiplied by 1.6. Get rid of that. And then we've got, and then we have the 2 pi radius, 0.25 meters, and the thickness, 10 meters. Right? So that gives us a velocity.
We should convert it to a second.
And we got to have some seconds. How many seconds was it in a day? Come on, guys. Huh? 86,000. Okay, 86,400 seconds per day. And you have to ask the question, why would someone know that number? No, obviously you have to use it, but okay. So we get rid of the day, and otherwise we got meters here and meters there. So this should give us meters per second. Of oil. In that 1968 Equifisk test, block 2.4, I can't remember all the well details. Well 2X, I think. Come on, help me out. You guys, come on. Don't make me do this.
1.00
How much?
1.9
Yeah?
times 10 minus 3.
Okay. Anybody else get the same number? Okay, good. All right. I always do a double and triple check, certainly on myself, but okay. So that's the velocity. So then we've got the diameter is, I said 0.5, 10 to the minus 6 meters. That's 0.5 microns. Velocity 1.9, 10 to the minus 3 meters per second. Density, I said 400 kilograms per cubic meter. And viscosity 0.2 millipascal seconds, 10 to the minus 3. Is that right? See, the 1.9, what was that? Oh, that was this meters per second. Let's see here. This should be our Reynolds number. Should be dimensionless. This is Pascal second. So the second cancels this, or not. Is this correct? Equation? D, velocity meters per second, density kilograms per cubic meter. Okay, so it's meter. Okay, and then the Pascal is, okay. What do we get?
That's correct.
And how much?
The number?
Yeah. It doesn't look like it's going to be greater than 1, but
Sounds a little way away.
Which is 1.9.
1.886.
2?
Raised to the power minus 3.
Okay. So that doesn't look good, so I'll have to, that looks too small. So I'll have to go back. In his paper, he actually gives the numbers he used in the calculation. So I'm just kind of guessing what the thickness and the pore diameter and everything was. But I'll go back and I'll find the paper and I'll either come back and say I made a mistake or something, but it definitely calculated something greater than 1 for it. So I'll come back to that. Maybe the rate was higher or something. Okay. All right. So that's my Easter. Yeah.
In the gas equation you showed earlier, the CPR square minus PWR square.
Yeah, this one here.
Yeah. Usually in this equation there is also one term n.
That we're going to come to. Yeah, it's related to Forsheimer. Yeah. Okay, so now let's move to using Darcy for gas. And the radial geometry, cylindrical radial geometry. We've got this equation. The velocity is equal to the surface gas rate, which I'm just going to write QG, times, we need it in reservoir rate, times BG. That will convert it to reservoir volumes over the 2 pi RH. Okay. And BG, hopefully you guys are remembering that, is given by this constant here, P over Z. Okay. So that's equal to QG, which I'm now just going to write, well, I'll write it surface. QG, let's collect all the constants together. PSC, TSC, reservoir temperature. We've got 2 pi H, like that. And then we've got Z over P. That's velocity. You have to help me if I'm missing something. And then that's going to be equal to our K over mu, dPdr. This is just a long, big expression for velocity. Okay, did I get it right?
Radius is missing.
Ah, the raises. Thank you. Put it out there. Okay. So now we're going to put all the QG here. We've got the 1 over R. We'll bring the dr over here. We'll move all the other stuff to the other side. We've got the 2 pi kh, standard temperature, standard pressure, reservoir temperature. And then we've got viscosity over here. We're going to bring the P over Z. So we're going to get P over mu Z. And we still have our dP on this side. Okay? So I think these are all the constants out here. Did I collect them all? And then we can just do the integration from the well-bore radius out to, we'll use the outer boundary, and we'll not worry about the average yet. We'll integrate here from PWF to PE. Okay. This is log RERW. Okay, the same stuff on the right. So then we can write kind of the final. I'm just going to write it QG. That's the way we normally do it. And we've got 2 pi standard and then we've got KH over reservoir temperature, log RERW. That's a log. Doesn't look like it, but log RERW. Okay. Times this integral. I'm going to do something here, tricky. I'm going to take that 2 there, put it here. No problems with that? Okay. This is basically a numerical constant, right? Since we know that standard temperature is 520 degrees Rankine or whatever it is in Kelvin, standard pressure is 1 atmosphere, so this is just a numerical constant. In addition, if we want to do it with all the units, okay, we've got unit stuff here, but this will all lead to a numerical constant, okay? And then we're left with this here, which is kind of our, if you want to call it a productivity index or a constant, that would vary from reservoir to reservoir, from well to well. The temperature could be different from well to well, the log RERW could be different well to well, and the KH certainly could be different from well to well. And then we've got this integral term here. So in and I don't remember when it was, but I think it was like early 1970. Maybe it was late 60s. There was a guy named, I don't know as Al-Hussein, and it may be Al-Husseini. This is terrible. I should know. I never knew the guy, so I don't know. But Al-Husseini?
He's an Iranian. I would expect.
Al-Husseini. I'll look it up. Oh, with an I? Yeah, I'll look it up just to be sure. This is terrible. It's kind of very important. Let's try to find this. It may be in Fetkovich's book. Let's see here. In the paper by Fetkovich. Let's see. References. Oh, there we go. Okay. Al-Husseini. R, I don't know what it stands for. Okay. And Ramey. And I think it was Crawford was also there. Crawford was another of the professors. Yeah, Crawford. This was when Ramey was still at University of Texas, Austin, I think, before he went to Stanford. And I think Crawford was a professor at Texas, also Austin. And Al-Husseini, I think it was his PhD work. I'm not sure. So what they did is that they introduced what was at the time called the pseudopressure, the gas pseudopressure function. Okay? and it was originally written M of P. Now the SPE requires you to write P of P. Okay, it's just changed the terminology. And this was defined as 2 times this integral of P over mu z dP from any reference pressure. It could be 0, 1 atmosphere, whatever you want, some reference pressure, usually 1 atmosphere, okay, to any other pressure, okay? So the actual function, 2p over mu z versus pressure, looks something like this. It doesn't have that little flip at the end, but it looks something like that. And if our external pressure is here and our bottom flowing pressure is here, then obviously this integral is just the area under the curve, right? But when we introduce this formal definition, going from, let's say, a reference pressure of 1 atmosphere, or 0, whatever you want, down here, then the total integral, this area under the curve that we show here, see this thing here, this is our P ref, right? So it's starting from here, going out to here. So if you take the whole area here, out to PE, then this is, that whole area here is M of PE, right? It's integrating from the reference 0, whatever, out to PE. And then if you subtract from 0 to PWF, which is down here, they call this something in integration, I don't know. But basically, if you take that whole integral there minus just that integral, that total ends up equaling what we want, right? Because this little area down here, you're getting rid of it there. Okay, so if we subtract, this is M of PWF, okay, the area for PWF. This is the area for PE. And if you take the difference in the two areas, then you get this integral that you want. So the 2 integral PWF PE P over mu z dP is equal to 2 P over mu z P ref PE minus 2 integral P ref to PWF P over mu z dP, like that. They call this something, and anyway, it's the same thing. But this we call either M of PE, or in today's literature, we call it pseudopressure E. And this is M of PWF, or what we today call pseudopressure at WF. So we can write, instead of this integral up here, we can just write it as pseudopressure external minus pseudopressure PWF. It's like writing two integrals. But what's actually done is, for a given gas reservoir, the PVT is assumed to be the same everywhere in the reservoir, and it's like you can calculate that integral once and be done with it. Okay? So we can come up with the pseudopressure function as a function of pressure just one time when we discover the field. and then you have this conversion from pressure to pseudopressure for all the other calculations in the field the rest of its life. That's the idea. So then you end up with this equation, which is gas, and then we've got this constant that was P, no, it was TSC, I don't know. Pi TSC. And then you've got the KH log RERW. And then you've got P pseudopressures, delta. What's that?
Reservoir temperature.
Yeah, the temperature, that's right. The temperature's got to be in there. Thank you. And that's... yeah. This is that numerical constant. This is a number that takes care of unit conversions and these three pi, TSC, and PSC. But you end up with a number here. All right? Depends on what your set of units is. Okay.
So in order to use this pseudo pressure, we should have a function or an equation for this P over mu Z.
Yeah, so what you have to do is that you have to, you basically have to have your pseudocritical pressure and temperature. You guys know about that from, it's basically a function of the gas composition, or maybe the gas specific gravity, its molecular weight. You have an estimate of the pseudocritical pressure and temperature of the gas. And then you just basically, from your initial reservoir pressure down to 1 atmosphere, you tabulate mu, Z, like that. You calculate P over mu Z times 2 in a column, and then you just do a simple integration, trapezoid or whatever you like. And then you've got this direct one-to-one correspondence. You could write an equation to go back and forth, whatever. So this is a pure PVT transformation. You do it once, usually. Now, I only know this number for one set of units. This is the set of units that I know. You guys can figure it out for your set of units, but I know it from my set of units. So I'm going to give you that, okay, without going through the whole mess. Okay, so for this in standard cubic feet per day, the number is 0.703 kH So the units here are millidarcy, feet, PSI, and degrees Rankine. And this has no units. Okay? So if you went through that mess that we did for the oil, it'd be a little different here because you got the TSC and the PSC. You'll end up with this number if you go through that same mess. Like I told you, I think Fetkovich in his paper he uses MSCF per day instead. And see if I can find his equation. Okay. Yeah, the problem is that he uses he doesn't use mu z, he uses 1 over mu g. So I'm going to have to he uses a different definition. It's kind of unfortunate because nobody else uses this definition. There's nothing wrong with it, but it's just, you know, you get rid of the TSC and the PSC, basically. But he uses a different definition, so I'll call it Fetkovich. And it's 1 over mu g BG from reference pressure in it. So the 2 is not included, and the TSC PSC is not included. It's part of the BG. So this ignores the 2 in the original definition, and the BG contains, if you will, the TSC and the PSC. Okay? And with those definitions, I think I'm pretty sure the rate is in. Let's see, he's got barrels per day. Man. You see here he's got the TSC, PSC. Yeah, unfortunately, he's got, I'm not sure what he's got in his, I thought it was, yeah, see, it's 1,000 standard cubic feet per day. Yeah, and then he finally, the familiar form, he's got this 3.57.
But here you have DSC and PSC.
Yeah, but you got TSC and PSC outside. So, yeah. But I think he's using 1,000. The main difference is that he's using 1,000 standard cubic feet per day. I think that's the main thing. You know, just be aware of that. Okay. So if we kind of assume this one's right, and we've got this set of units that we're talking about here, then I'm going to transform this This is a steady state equation. That's the assumption that's been made, is it's steady state, because we're using this external boundary. And if we want to write the pseudo-steady state, or the so-called boundary-dominated standard equation, then we're going to use average reservoir pressure instead of PE. And we're going to add skin. To the equation. Okay. And then we're going to get something that's looks like this. Pseudo pressures, average pressure, and then we've got reservoir temperature, log RERW minus 3/4. That's because we're using average pressure here, and it's got a no-flow outer boundary, plus skin. Okay. And again, we reiterate that this is for Darcy flow only. So it'd be at lower velocities, that we haven't exceeded this Reynolds number. So units, standard cubic feet per day, millidarcies, feet, PSI, degrees Rankine. So. Okay. Let me just make a comment about the way this function looks, this P over mu z. Okay. You can put the two in front of it if you like. It's always going to look something like this. It's going to be kind of linear out to about 100 bar. Around 100, 150 bar. And then it's going to kind of start turning like that out to about 300, maybe 250 bar, maybe not to scale. And then it's going to kind of, actually that's probably more like 300 bar. And then it's going to kind of just not drop very much, but you can go to very high pressures, but it's going to be almost constant. It'll decrease some, but it'll be almost constant. Okay. So above about, I think Fetkovich says 3,500 psi, which is I think around 250 bar, kind of. If you kind of take this out here, around, what's 3,500 divided by 50? It's about 250, I'd say, 250 bar-ish. Okay. Then it's more or less constant. And if we said that it was constant, let's say that it was constant everywhere, you know, kind of as an approximation. If you said that, you know, this constant would be a pretty good assumption for all the way from way out here to, so this is kind of a constant. Where it's actually like that, you can just use delta P, PR minus PWF. It's, okay? But what you see is that in reality, as the bottom of flowing pressure drops down below this 250, the actual area under the curve driving the rate, okay, let's say we're at a reservoir pressure here, down to a bottom flowing pressure here. Okay? Because of this low pressure behavior, we're not getting this area, right? If it had remained constant, you would get that area. So it'd be a higher rate. So what you can say is that the amount of rate that you get per bar pressure drop, okay, which is our PI, kind of our PI, was stock tank barrels per day per PSI. So if we think of this as a simple IPR equation where we just use average pressure PWF, which is not correct, then what you could say is that the J if we plot G from this incorrect equation, then effectively that it would be more or less constant here, okay, when the flowing bottom pressure is to there, but then as you drop down below this, where it starts dropping down here, this thing is going to go down like that, okay? Your effective productivity index for a gas well will in fact be pretty much constant at high pressures, but then as you draw the well down, you get less standard cubic feet per day per PSI, okay, per drawdown. So you lower the pressure at the bottom of the well, but you don't get as much gas as you do up here. So this is kind of reflecting our effective productivity index of gas. And for practical purposes, as long as PWF is above 250 bar, then that's basically a constant. But as soon as you drop below it, then you get less gas rate per drawdown. Okay. Okay. So I'll put this in red since it was kind of this discussion of. Okay. All right. So we'll take a break and then we'll come back and kind of generalize it for the non-Darcy situation of Forshine.